So, today we have two things to accomplish. One, I want you to become familiar with the 6 trigonometric ratios of sine, cosine, tangent, cotangent, secant, and cosecant. In addition to that, we're going to use sine, cosine, and tangent, the first 3, to find unknown side lengths in a right triangle. That's what we want to take care of. Now, SOHCAHTOA, that's right. For my benefit, how many of you have done right triangle trigonometry at some point in your past? Okay? All right. We're going to start from scratch. But if that's the case, if you're one of those people, many of the things will be somewhat familiar. The first thing we have to note is this. Everything that we're going to do this week is concerning right triangles. And if you have a right triangle, we have to decide which angle is our point of reference when labeling sides with names. Okay? First of all, since we're working with right triangles, the hypotenuse is always, as it has been in the past, the longest side. But we need to choose, when we're working with the right triangle, we have to choose one angle to work with that's going to be our reference, our starting point. Now, sometimes one of the angles will be given, sometimes it won't, but in any case, we want to choose an angle. Now, for this example that's on the screen, we're going to choose our reference angle, theta, to be the top left angle, the larger of the two acute angles. And we label the remaining two sides according to our choice of that angle. The opposite side is the side that does not contact our angle that we've chosen. Okay, so since we chose this to be our angle, the opposite side has got to be the bottom one. The adjacent side, well, what does adjacent mean? Next to. Adjacent means next to, and so the adjacent side is the side that is next to our angle. Of course, there will always be two sides adjacent to our chosen angle, but one of them is always going to have to be the hypotenuse. So the adjacent is the leg that is next to our chosen angle. That naming system is the basis of pretty much all of trigonometry. So it's a pretty simple concept, but very fundamental. So before we go on and solve any triangles, let's just take a minute and label these sides. In relation to that 32-degree angle, let's label our opposite, adjacent, and hypotenuse. Okay, 32 degrees. That's our top right angle. Now, according to this angle being our reference of 32 degrees, this angle has to be which one? Opposite. This one has to be the adjacent. And of course, this is our longest side. It's opposite the right angle. It has to be the hypotenuse. Okay? Well, that sets us up to establish some trigonometric ratios. Okay. Good so far? Sure, no problem up to there. Now, the second thing that trigonometry is based on, and there's kind of an interesting historical perspective to this, is that no matter what, if you have two or more triangles and one of their acute angles is equal, then those triangles have to be similar. They have to have the same proportions and the same basic shape. Now, if you think about this for a minute, how do you suppose this was first discovered? There's a logical place where this was first discovered. Does anybody know what branch of science most mathematics was created for? What branch? There's one particular branch of science that historically had a need for mathematics that was not being filled. Astronomy, yes. Astronomy was one of the earliest sciences to really be developed. It was astronomy. Well, astronomers were very concerned with things like star angles and sun angles and whatnot, and it was noticed pretty early on that if you had the sun casting a shadow from a tree or a post or anything else, it was discovered early on that the length of the shadow had the same proportion to the height of the post, no matter what the height of the post. So for example, if the sun was at a certain angle at a certain time of day, and it cast a shadow that was twice as long as the post, it would do that for any post. Didn't matter. Well, really what that did was it established the principle of similar triangles. And that if that sun angle was the same, in that case this would be right here, theta, our angle of elevation looking up to the sun, as long as that was the same for every shadow, which it was at the same time of day, those proportions would always be the same. Well, it's also noteworthy that the very first ratio that people were interested in was the ratio of the pole, or in other words, for this right triangle, the opposite side to the adjacent side. That was the first ratio that was of particular interest. Getting back to the topic up here, we know that as long as two right triangles share one acute angle, they've got to be similar. So you can see I've got two similar triangles up there. You can see that the larger one has the same 61.93 degree angle. It's just that all the sides are doubled, twice as big. Now here's what that does for us. We're going to establish a ratio. We're going to call it the sine ratio. And the sine ratio is going to be the quotient we get when we divide the length of the opposite side by the hypotenuse. Now, which side in a right triangle is always going to be the shorter of the two, the opposite side or the hypotenuse? Opposite will always be shorter than the hypotenuse because the hypotenuse has got to be the longest. Therefore, when you take the opposite and divide it by the hypotenuse, you're always going to get some decimal value or some fraction that's less than 1. And that ratio we're going to call the sine ratio. Let's do an example. If you have a calculator with you today, take it out. We're going to take a look at two similar triangles. And we want to pay particular attention to the opposite and hypotenuse sides for these two triangles. Here they are. There's our two triangles. Same ones that I had up just a minute ago. We want to evaluate what the sine ratio is for 61.93 degrees. First of all, the angle that we're referencing is the one in the top left, 61.93. We know that for a larger triangle, we've got 160. Let's take the larger one. We know that the sine ratio for 61.93 degrees is going to equal what over what? Opposite over hypotenuse. So we're going to take this opposite side length from 61.93 degrees, 300, and divide it by 340. Now, take your calculator and divide 300 by 340. You're going to get some value. We're going to round it off at 4 decimals. You should get about 0.8824. Okay, 8824. Now let's do the same thing for the smaller triangle. Down here, the sine of 61.93 degrees is equal to opposite, which is 150, divided by 170. Divide that out and you get 0.8824. Well, do you have any theories about this 61.93 degree angle? Any triangle that has that angle, a reference angle, or an angle of 61.93 will always have an opposite over hypotenuse ratio of 0.8824. Now your calculator knows this. That's why when you take your calculator, make sure it's in degree mode first of all. Put your calculator in degree mode. Once it's in degree mode, you can type in 61.93 degrees and just hit the sine button. It'll tell you what the opposite to hypotenuse ratio is for every triangle where your angle of choice is 61.93 degrees. And if you hit the sign button, your calculator says it is 0.8824. All right? So we have this calculator basically serves as a tool or a table to tell us what the ratio is for any particular angle. All right. Well, the two other ratios that we can form, if you think about the fact that we have three sides, if we take different combinations, we used opposite and hypotenuse, we can take the adjacent divided by the hypotenuse. That gives us what's called the cosine ratio, abbreviated COS. That's the adjacent over hypotenuse. And the third one is the tangent ratio. Tangent of theta was actually the first trigonometric ratio of interest because of the height of pole to length of shadow ratio that we talked about earlier. The other two follow a little later. And tangent is equal to opposite over adjacent. Well, these you need to have these memorized. Going to be common as dirt for the next 5 weeks and beyond. But, Aaron, I think you said it before. What's the little trick that some of you probably have also known this trick? What's the way to remember these ratios? SOHCAHTOA. You can remember that the sine ratio is opposite over hypotenuse. The cosine ratio is adjacent over hypotenuse. The tangent ratio is opposite over adjacent. And we have SOHCAHTOA. That's probably the most widely used trick for remembering the 6 trig ratios. We want to establish what the cosine and tangent ratios are for those same two triangles that we used just a minute ago. Again, 61.93 degrees. This time we'll just use one of the triangles. Let's use the larger one. Well, based on this fact, we can claim that the cosine ratio, the cosine of 61.93 degrees, is equal to, cosine represents what over what? 160, the adjacent side, over the hypotenuse of 340. 160 divided by 340 is going to give you 0.4706. Now check that. Take your calculator and just type 61.93 and hit the cosine button. Verify that it does give you about the same thing, Drew. Okay. Does it give you, I think this one's slightly off. What do you get when you type 61.93 degrees and then hit cosine? Isn't it 4704? Slightly off. Why is that? Any theories as to why your calculator answered very slightly from this one? 0.4705. Close enough for our purposes, but the reason? With these three sides, that is not exactly a 61.93 degree angle. That's rounded off to 4 sig-digs, and so that's only a good approximation our picture is. Well, the last one, tangent of 61.93 degrees, is going to be equal to what over what? Opposite of 300 over an adjacent of 160. And that gives us 1.875. Verify that by typing 61.93 degrees in your calculator, hitting tangent. I think that one works out very close. Okay. So ultimately, when you go to hit the sine, cosine, or tangent button on your calculator, what you're really doing is you're asking for a ratio for some particular triangle. Okay, well, let's go ahead and solve a right triangle here. I've got a triangle drawn with a 38.4 degree angle down in the bottom, and the top edge is 9 feet 4 inches. We want to figure out what the unknown angle and side lengths are for that triangle. Let's just put all of our units in inches. 9 feet 4 inches on the top, that's 112 inches up there. Okay, well, Let's complete that triangle. First, let's find the sides first. Okay, there's a reason for this. We'll come back to it in a minute. Let's say that the adjacent side here, let's call that A, and hypotenuse we'll call H. So we want to find, let's start with the adjacent side. We know what our reference angle, or our angle of choice here, 38.4 degrees, this is going to be our angle. We know that we know the opposite side, and we're trying to find the adjacent side. So you need to choose which trig function will deal specifically with opposite and adjacent. Tangent. So we can conclude then that the tangent of 38.4 degrees is equal to the opposite side, which is 112, divided by the adjacent side, which we don't know. We know that the tangent of 38.4 degrees, that's going to be a ratio, is equal to 112 over A. Now we just solve for A. So you go and get your calculator. 38.4 degrees and find out what the tangent of that is. Calculator says that that ratio for a 38.4 degree angle is 0.7926. Trigonometric ratios are almost always written with 4 decimal places, 4 sig digs. Just customary to do that, no particular reason for it. That's equal to 112 divided by A. Now, I'm going to point out a very common algebraic trick that you're going to be using dozens of times over the next week, and it'll save you a lot of algebra. If we wanted to solve this for A, what would you typically have to do? Multiply both sides by A. And then divide by 0.7926. You'd get A equals 112 over 0.7926. When your unknown is in the denominator, you can, instead of going through that multiply and divide process every time, you can just do the switcheroo, all right? When you've got A equals B over C, you can just switch these two values around and the equation will still be true. That's going to save you writing that algebraic step over and over and over dozens of times over the next couple of weeks. So we just do that switcheroo, and A is equal to 112 over 0.7926. Well, then you can compute that, and that A value is equal to let's see here. 141.3. That's leaving an extra decimal on there. Anybody else get the same thing? 141.3. Okay, so we've got this side. We're going to blow off significant digits here for a couple of examples and just leave extra precision. And now let's find B. Now to go on, now you could, it's worth noting that you could throw trigonometry off to the side and just use what to find our hypotenuse at this point? You could use the Pythagorean theorem. What's the only real problem with the Pythagorean theorem? It's what? Well, it's just as accurate if we know that this is right. But rather than use Pythagorean theorem, in which case, if we would have maybe made a mistake here, is there any hope of finding the correct hypotenuse using Pythagorean theorem? No. Once we use an angle or a measurement that we found now, if it's wrong, everything will be wrong. So what we try to do is always use the given information at each step. So even though we know this, we're going to ignore it and go back to our given information, because that, hopefully, is error-free. So what trig function do you want to use to find h now? We know the opposite. We want to find the hypotenuse. Sine of 38.4 degrees has got to be equal to the opposite, which we know to be 112, divided by hypotenuse. We know what sine of 38.4 degrees is. 0.6211. That's 112 over h. Do the switch, and we've got h equals 112 over 0.6211. tells us our hypotenuse is 180.3 inches. Again, we're just going to leave an extra significant digit on there. We found all the sides. All we've got left is one angle. Well, that's no trouble at all. What's that other acute angle need to be? 51.6 degrees. Why, Steve? Yeah, and specifically in right triangles, since one of them is always going to be 90 degrees, the other two acute ones always have to add up to 90. Okay? 51.6 degrees. So it's going to equal 38. The two acute angles have to add up to 90, so ours has to be 51.6 degrees. Now, you could have found that to begin with, but any ideas as to why it's sometimes better to just leave that angle and do it last? That's one reason. Also, what if you, here again, if you put the 51.6 here, you might be tempted to make this your angle of choice for setting up your adjacent and opposite, which you could do, but if you accidentally do some subtraction wrong and use this one, everything else is wrong from there on out. So always try and use given information, and don't use information that you've already found, if possible. We're done. We've found all the parts. Get to those next week. Okay, take just a minute. Never mind, we're going to do this one together. This time, same principle, but this time our angles in radians. Determine the unknown angles and side lengths for this triangle. Okay, well, label your sides. The top right has got to be opposite. Whoops. That side's got to be adjacent. So we'll call the opposite side, don't call the opposite side O. Bad variable. We'll call it P for opposite, and the adjacent side we'll call A. Okay, well, let's find the opposite side first. We know our angle. Even though it's given in radians, we don't do anything differently. We can just say that the sine of 1.09 radians. Incidentally, it's very common when working with radians to just leave the units off. That's why if you're working with degrees, it's imperative to make sure you put the degree symbol, because any angle without unit shown, the default is that it's in radians. Pretty common notation. So we'll follow that. 1.09 refers to 1.09 radians. That's equal to the opposite side, which we don't know, over the hypotenuse of 855. Now, is this a case where we're going to do our algebraic switcheroo trick? No, you just multiply both sides by 855. Now, the only thing, we don't do anything differently except for the fact you need to make sure that your calculator is in radian mode. So when you ask your calculator what is the sine of 1.09, it knows you're talking about 1.09 radians and not 1.09 degrees. Sine of 1.09, if you're in radian mode, times 855 should give you 758 millimeters. You could. I'm not, because I want you to pay attention to the angle and switch your calculator accordingly. You know what the number one mistake for these first few topics in trigonometry is, incidentally? Number one mistake. Every semester I see it. Not changing your mode. You're doing a couple problems in degrees, and then you hit one in radians, and you don't change the mode on your calculator. First thing I check, if when on the homework or test or something, when you're doing, if you get a problem wrong, the first thing I do is I work the problem assuming that the calculator's in the wrong mode, and most of the time that's what it is. So watch out for that. So P is 758. Okay, that takes care of that. The adjacent side, which trig function are we going to use here? Cosine of 1.09 radians has got to equal the adjacent side over the hypotenuse. Cosine of 1.09 radians times 855 should give you an adjacent side of 395. Yep. Now, though we don't use the Pythagorean theorem, it would provide an easy way to check. We could now quickly take our adjacent squared plus the opposite squared and make sure we get the hypotenuse squared. We won't do that, but it's worth noting that we could. Now, the last thing we have to do is figure out this angle in radians. What's that angle got to be? Think about that for a minute. Don't let your mind wander to degrees. We won't use degrees as a crutch here. Think about radians. What does that angle have to be in radians? Well, let me ask you this. Think about degrees for a minute, right after I told you don't think about degrees. But think about degrees for a minute. What's the sum of the three angles in a triangle have to be in terms of degrees? 180. All right? Well, 180 equates to how many radians? Pi. Pi radians, right? So for a triangle in radians, the three angles don't have to add up to 180 degrees. They have to add up to pi. All right? Well, what's 90 degrees? This 90-degree angle is actually not 90 degrees. It's, what's 90 degrees? Pi over 2. Good. Pi over 2. So we know that this angle is going to be pi minus pi over 2 minus 1.09. And pi minus pi over 2 minus 1.09, 0.48 radians. Which means, to shortcut that rule just a little bit, just like when we said if its total is 180 degrees and that angle's always 90, the two acute angles always have to add up to be 90 degrees. We can shortcut that and say since this is always going to be pi over 2 in a right triangle, what do the two acute angles in a right triangle have to add up to in terms of radians? They have to add up to be pi over 2. Okay, they always have to add up to be pi over 2. So we could take pi divided by 2, subtract 1.09, get the same result. We will usually be working in degrees, but it's worth noting that we don't have to. In general, when you're dealing with any triangle, this doesn't apply to just right triangles, but any triangle, angles are frequently referred to using either Greek letters, theta, beta, alpha, or commonly capital letters. It's very rare to refer to an angle as a small letter. So, for example, if we have this triangle and we refer to that angle as A, B, and C, we better use capitals. The side lengths, segment lengths, are always referred to using lowercase letters, and typically so that opposite sides and angles share the same letter. So, for example, if I decide that this is angle A, this has to be side A. If that's angle C, this has got to be lowercase c. And if this angle is capital B, its opposite side is going to be lowercase b. Your homework for today uses that notation. They give you side lengths A or B, and then one of the angles. Also, if it's a right triangle, capital C is always the 90-degree angle. Why do you suppose that is? Because what? Right, exactly. And following with the Pythagorean theorem, that if we're talking about a right triangle, C really should be the hypotenuse. And that being the case, since C is the hypotenuse, it has to be opposite capital C, which would have to be your 90-degree angle. So the notation holds for all triangles, but if we're dealing with a right triangle, we call capital C the 90-degree angle. Okay. Well, the three Kind of less popular cousins of sine, cosine, and tangent are cotangent, secant, and cosecant. They kind of get forgotten a lot. At Christmas time, those are the three that don't get greeting cards. They don't get invited to the cool parties. But they do have significant importance for math later on. We don't need them particularly to solve right triangles because the three combinations of sides, with three sides, pick two. There's only three ways to do that. Sine, cosine, and tangent cover it. But they do have uses later on in calculus. And so when there's an important point to make about these three, we do it. Otherwise, we just kind of leave them off to the side. First of all, the cotangent ratio takes the tangent ratio and flips it upside down. But the cotangent of theta is adjacent over opposite. The secant of theta is the hypotenuse over the adjacent, which is the reciprocal of the cosine function. And cosecant, hypotenuse over opposite, is the reciprocal of the sine function. Now I'm going to show you an easy way to remember those. If you can remember sine, cosine, tangent, you can remember these three with very little trouble. Here's how. Here's the trick to remember these three alternative functions. First of all, you got to know sine, cosine, and tangent. If you don't know those, well, things aren't looking good. Once you know these three, though, the other three follow. All you do is think of all six of them in order. Sine, cosine, tangent, cotangent, secant, cosecant. Now, they form reciprocals of each other according to this pattern. These middle two are reciprocals of one another. So if you can remember the tangent of theta is opposite over adjacent, it's the third function. The fourth one will be the reciprocal of that, or in other words, adjacent over opposite. More importantly, since it is adjacent over opposite, that's the reciprocal of the tangent function. We say that it is 1 over tangent of theta, just like is shown on the screen. Well, the secant, the fifth one, is the reciprocal of the second one. So cosine theta is the adjacent over hypotenuse, then secant is hypotenuse over adjacent. But again, more importantly, it's the reciprocal of the cosine function. And it's that tool that'll let you use your calculator to evaluate these because there's no cotangent secant or cosecant buttons to be found. And that leaves sine. The first and the last trig functions also have to be reciprocals of one another. So cosecant theta is hypotenuse over opposite, or in other words, the reciprocal of the sine function. That's the trick that I still, to this day, when I see secant, I think in my head, okay, secant is the second to the last one. That's the reciprocal of the second one, which would be hypotenuse over adjacent. Now, we're just going to see how to handle cotangent secant and cosecant on your calculator, and we're going to call it a day. Questions about those three, their definitions? All right. Well, let's jump to a couple examples here. Whoops. Let's evaluate the secant of 32.6 degrees. Secant of 32.6 degrees, we're going to find, there's no secant button on the calculator, so we need to take and find what's the reciprocal of the secant function? Cosine. So that's going to be the same as 1 over the cosine of 32.6 degrees. Now, a calculator trick. If you have a graphing calculator or a regular calculator, you've got a reciprocal button on there. Use it. There's no need to type 1 divided by, though you can. You can just do 32.6 on your calculator, hit the cosine button, and then find the 1 over x button. That button might look like a couple of different things. It might look like this. It might look like this. 1 over x, x to the negative 1. If you've got a graphing calculator, it's the x to the negative 1 key. 32.6. Hit the cosine button and then 1 over x. And for this one, you should get 1.1870. Take a minute, find the cotangent of 68.25 degrees. Cotangent of 68.25 is going to be 1 over the tangent of 68.25 degrees, which is, anybody get that? 0.3990, that's right. 0.3990 is the cotangent of 68.25 degrees. Another one, find the cosecant of 1.384 radians. It's going to be 1 over the sine of 1.384 radians. You should get 1.0177. Just a notational issue. How are exponents of trig functions written? They're written a little bit differently than you might expect, and it's important to at least recognize this. If we want to evaluate sine squared of 25 degrees, what that means really is that we want to take the sine of 25 degrees and square it. The exponent is written after the sine function and not the 25 degrees. Why do you suppose that is? Well, what if it wasn't written there? What if it was written on the number? Would that be the same as sine of 25 squared degrees? Absolutely not. This says you should take 25 and square it. That's not what we want. We want to take the sine of 25. So what we typically do, what I do, is I rewrite it as sine of 25 degrees in parentheses and square it. So this is all calculator work. Take sine of 25 degrees, hit the squared button. You should get, I have 0.01786. Anybody get 0.1786. That's what you should end up with. So that's how we can handle exponents of trigonometric functions.